right, so we have possibly a dehumidification process here for problem 10. We've got atmospheric air coming in. We're given a relative humidity, we're given a pressure, we're given a temperature. I've also written kind of, when we've shown this before, that the mass flow rate of the moist air of that ideal gas mixture, it's equal to the sum of the mass flow rates of each of the components. And of course, you've got two. You've got the dry air and the water vapor. So all of that's coming in, and it passes over this cooling coil, and it removes heat, and it comes out, the atmospheric air comes out at 15 degrees Celsius. The way that it's removing heat is by circulating refrigerant through that cooling coil. So you've got the refrigeration coming in on the left and going out at the right. And they tell us that the change in specific enthalpy of that refrigerant, so delta little h, is 100 kilojoules per kilogram. So that would be the H of the refrigerant going out minus the H of the refrigerant going in. And then they also say any condensate, if there is any condensate exits at 15 degrees Celsius. And so what we're looking to find, they say that we want to find the refrigerant flow rate, but they want it, it's kind of strange because they want it in kilograms of refrigerant, kilograms per kilogram of dry air. So what they're really asking for is the ratio of that m dot of the refrigerant over the m dot of the dry air. So I've kind of shown that the units will work out to kilograms of refrigerant per kilogram of dry air like we want. And they do tell us that we can, that we can ignore kinetic and potential energy changes, and the only, Q dot, all that heat transfer is going from the moist air into the refrigerant, so we don't have any heat. There's no heat loss out of this entire system. So I've thrown all my assumptions. Delta kinetic and potential energy are 0. I might want to throw on there that, that moist air behaves as an ideal gas. That would probably be good. And so I guess I'm ready to go through and get my solution. The first thing that I probably need to do is figure out, do I have any condensation? So let's go ahead and do that. So do you have condensation? So there are two ways that we can do this. One is by calculating what the dew point temperature is. There we go. So we can calculate what the dew point temperature is. And for that, we'd use our relative humidity at 1, and we'd just see if we cool below it. But the other way is if it's at 1 atm, if our atmospheric air is at 1 atm, then we can use our psychrometric charts, and that's what we're going to do because we're at 1 atm. So we're cooling from 30 degrees Celsius with a relative humidity of 80% down to 15. So 30% relative humidity of 80. So I got a little picture of a psychrometric chart here. So let's see. So 30 degrees, that's my T1. And then my relative humidity is 80. I'm just gonna mark a little thing right there. Kind of have to draw my way up here because otherwise I'll lose my eyes will cross. See, even now they're crossing as I get right there. But okay, so that looks good. So here's my state 1. So I've got a relative humidity of 80%, T1 is 30 degrees, and then I'm cooling down to, let's see, I'm cooling down to 15. So 15 degrees Celsius. So as heat is removed, it's going to cool, no condensation. But then as soon as it hits this line right here, in order for me to get down to 15 degrees Celsius, it does have to condense. There's no way for me to cool along a line of constant specific humidity. So there I am coming out at state 2. And so now I've drawn my, I got my states kind of fixed here, if you will. I don't really like that. There we go. Now I can actually see what I've written there. All right, so there's my state 1 and state 2. So yes, I do have condensation. So I guess we'll go up here answer the question here? Yes. And we've just shown that. We've shown why. So what we're going to do is we're going to apply our conservation of mass. Let's do that first. And we can do it for the components as well as the mixture. We're going to do it for the components here. So for the dry air, I've got m dot A at state 1 coming in, and then got m dot A at state 2 going out, and that's just going to be m dot A. And by the way, when we're looking at that, when we're looking at the conservation of mass, we're not looking at the refrigerant, because the refrigerant can't physically cross the coil, the physical boundary. So just kind of keep that in mind. So that's why you don't see that there. And then for the water, you've got water vapor coming in with that moist air. You've got water vapor going out, but you've also, and we've just shown this, you've also got m dot W, which would be the mass flow rate of that condensate that's coming out. And so I might want to actually put things, define that m dot W. So that would be m dot V1 minus m dot V2. And we've shown this a couple of times that I can isolate m dot A on the outside, and I'd have to multiply m dot A times m dot V1 over m dot A in order to get what I need to get. And this would be the specific humidity at state 1. This guy would be the specific humidity at state 2, right? And once again, that's because this would be m dot V1 over m dot A, right? I'm gonna just kind of erase that. There we go. All right, so I've applied my conservation of mass. Now I'm gonna apply my conservation of energy. All right. So we've got things coming in, right? Of course, my conservation of energy is going to give me, I'll have Q dot equals, what do I have? Q dot is equal to the sum of the m dot H's going out minus the sum of the m dot H's going out. So that's the first law for an open system. I ignored kinetic and potential energy changes. I also said that W dot is equal to 0. Somewhere in the problem statement, it did say everything was operating at steady state. So I could put that in my givens, or I could throw that in the assumptions and be done with it. All right, but we do need to figure out this Q dot probably, or maybe do something with that. Actually, there's a couple of things that I could do here, couldn't I? So this guy right here, let's do this. This guy right here, this is if my control volume excludes the refrigerant, right? So what I mean is, and I'm going to draw a solid line because I want to be able to erase this easily. But what I'm saying is I draw my control volume so it's just around the atmospheric air that's coming in and out, and the condensate that's also going out. And that way I capture that Q dot that's crossing the system boundary that I've drawn in green. But I think it's going to be clear, and the reason that I would do that, why that would help me, is if I solve for that Q dot, then maybe then I just draw my control volume around this guy. And then I say, okay, well, the Q dot leaving the moist air has to be equal to the Q dot going into the refrigerant. I put them equal to one another, and I solve for what I need to solve for. But I think there's a little bit cleaner way, and so I'm going to do that now. So I'm going to this is a nice thought, and it's okay, it's fine, I could do it. But let's do this. Let's draw our system around everything. Oops. Okay. So if I do that, and now I'm going to actually draw a little dashed line here. So I'm going to draw the whole, let's draw it around the whole thing. So now, when I draw my control volume around that, the Q dot is actually, for that control volume, Q dot's equal to 0, right? I have heat transfer within the system boundary, but it's not crossing that green dotted line. It's not crossing the system boundary. So I won't have that in my equation. And so when I apply my first law, all I'm going to be left with is that the sum of the m dot h's coming in equals the sum of the m dot h's going out. So now let's kind of look at what I've got. I've got quite a lot of inlets and outlets. So, okay, so going in, let's do that first. So I've got m dot a HA plus m dot v HV. This is the inlet. This is coming in at state 1. That's that moist air. And then also going in, I've got m dot of my refrigerant, enthalpy of my refrigerant going in. All right, and then I've got the outlets. All that's equal to the stuff going out. So make this a little bit, because I'd like to keep everything in the picture as much as I can. Then I've got things going out. So I've got the moist air going out. So let's handle him first going out. So I've got m dot a HA plus, and that's a dot, m dot v HV. That's the moist air coming out. Plus, I've also got, let's put that one, m dot of that condensate, which remember, I've actually defined him right there. So I won't forget that. M dot W, HW. And then of course, I've got one more thing going out, and that's the refrigerant. So it'll be m dot of my refrigerant, enthalpy of my refrigerant. Oops, capitalize that. And this would be going out. So now you can see sort of where we're going, and you can see why it's going to be really useful to us if we can kind of isolate that m dot a on the outside as best as we can. So let's get the m dots of the refrigerant kind of on one side. So I'm actually going to do out minus in because I've got things in terms of delta H's, so, or delta of the delta H of that refrigerant. So this is going to be m dot of my refrigerant times the enthalpy of the refrigerant going out minus the enthalpy of that refrigerant going in. And this is going to be just m dot of my refrigerant times delta H of my refrigerant. And remember, if we kind of look up here, that's something I know. It's the 100 kilojoules per kilogram. Okay, perfect. But that's also equal to, let's go ahead and take care of everything else. So I've got m dot a HA plus m dot v HV. All, let's see, this is coming in, that's a H1 minus, right, oops. I'm just kind of moving things around. M dot A HA plus m dot V HV at 2. And then of course I've got this guy right here, the m dot W. I'm going to go ahead, and this is going to have to come over on the other side. I'm going to go ahead and put that in terms of this right here. Okay, so then this would be m dot A times the specific humidity at 1 minus the specific humidity at 2. All right, I'm almost there. And then this becomes, I'm going to isolate m dot A on the outside. Okay. So we've seen this before, right, with the simple heating and simple cooling. If I isolate m dot A on the outside of this guy, it becomes HA plus the specific humidity, right? This is at 1. Then I've got the next guy, HA plus, oops, the specific enthalpy of that moist air at 2 minus, open, I think I forgot something. I did. There we go. Somebody's probably screaming at their computer like you forgot it. So there we go. Okay. So I think we're all good there. So I can, I can clean this up a little bit if I want to, and I think I will, just because I want to rewrite it and make it pretty. But I'll have m dot of my refrigerant over m dot of that dry air. Okay, so then, let's see, I'll have a big long term over here. So this is going to be, oops, it's just going to be the specific enthalpy of that moist air at 1 minus, same thing, oops, same thing at 2 minus, whoopsie, minus the specific humidity at 1 minus the specific humidity at 2. I guess I'll keep that color, but this is the enthalpy of that of the condensate. And then of course I'm dividing all of this by delta H of that refrigerant. So I think I'm good. That was a big long equation to get things into a nice simple form. And I think I've done everything correctly. Let's make sure that I didn't mess up. I think we're good, actually. So this is in. Oh, that's out minus M. Yep, I think we're good. So let's go ahead and get those other properties then. So I'll say where. Let's get the specific enthalpy of the moist air at 1, the specific enthalpy of that moist air at 2. We'll also have to get the specific humidity at 1 and the specific humidity at 2. We're given that delta H. And then that HW, by the way, this is that condensate. And so we're going to approximate this as H sub F at TW, and that TW was given to us. And I'll go ahead and give you this guy. So this is going to be the H sub F at 15 degrees Celsius. And I've got 62.99, and it's kilojoules per kilogram. So you can find that in table A2. So A2. But these other guys we can get from our psychrometric chart. So let's go look at it. So I need specific enthalpy, and then I also need the specific humidity. So this looks to be 1, 2, 3, 4, 5, I don't know, about 85. I guess depending on which way I'm looking at it. And then at state 2, looks like this is gonna be, it's like right kind of close to 42. maybe 41. I can't quite, maybe I kind of draw it like that. Sort of looks like maybe 41. Yeah, remember, you're reading it off of a chart. So, you know, if you read 41 versus 42, it's not like I'm going to split hairs, because sometimes when I look at it multiple times, it ends up that I'm seeing something different, slightly different every time. For this guy, 0.0215. And then this guy, about 0.0105. Right? Yes. Okay. So I'll go ahead and maybe throw that on there. So at state 1, it's about 85. At state 2, it's about 41. This guy is 0.0215. This guy is 0.0105. Right, this guy is kilojoules per kilogram of moist air. This guy is kilojoules per kilogram of moist air. And so when we plug everything in, you should get something about 0.44. And it's kilograms of refrigerant per kilogram of dry air. Okay. That was a lot of work. A lot of work on the derivation side, and that's why it's really important to kind of be comfortable applying your first law in conservation of mass to get those equations. All right, well, thank you so much for watching. Let me know if you have any questions.